A2. More than likely, I'm going to go on the assumption that it's B that was tripping people up the most. And we'll talk. We can talk about that, right? But in these cases, the biggest thing really to figure out, right, is just simply that you're going to be using two equations for the most part, right? The first equation is going to be, the conversion of, speed of light is going to be equal to the frequency times the wavelength, right? So C is equal to nu times lambda, and then the other one is going to be, energy of a photon is equal to, hc over lambda, or h times nu. Right, so those are the two main equations that you're using in these two cases. So right, for A, since we're going from 500 meters to hertz, right, that relationship is then going to be related to the speed of light is equal to nu times lambda. And so we have the wavelength, right? We have meters, and we're trying to go to hertz, and so we can rearrange that equation so that what we have is nu is equal to c over lambda. So we just simply do 2.9979 times 10 to the 8th meters per second over the wavelength, right? So that's going to be 500 meters. So that will be equal to 2.9979 times 10 to the 8th divided by 500. So that comes out to being, 5 point, what am I at, 3 sig figs? Well, I guess technically I'm in a way only at 1 sig fig, right? But it comes out to being like, 599. It's a lot of nines. So 6.00 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th per second, right? Or hertz. Hertz works as well in that case. Right? Yeah, 600,000 hertz. 6 times 10 to the 5th per second, or hertz, right? That's the exact same thing. Now here, the one that I think that was tripping up people the most, right? So so reciprocal centimeters, if we is a unit that is very commonly used in spectroscopy to proxy energy, right? Because if we're looking at this equation right here, right, if we look at energy is equal to hc over lambda, what you can do is, right, you can just simply pull out the hc, and then you can have 1 over lambda right there, right? Because h and c are both constants, right? So they don't change at all. And so because, and I talked about this when I was talking about both D1 and D2, and also when I was talking about, I think it's B2. If you haven't looked at those videos yet, right, when you're the relationship between wavelength and energy, right, is an inverse relationship. And when you're calculating and you're looking at and trying to figure out like what is, how is like one, photon or whatever, or some kind of absorption, or photoelectric effect, if you have one happening at like one wavelength, right, you need this wavelength of light for it to go, and you have another one happening at a different wavelength of light, those, that difference doesn't directly scale linearly, right? You can't simply subtract those two wavelengths and then get, what an accurate energy is, or an accurate like relationship in terms of, the energetics of what's going on. And so you always have to convert those into energy. And so the easiest way that you can just simply, scale these things for yourself is just, to use reciprocal, wavelengths, right? Which is what you're doing here, right? So reciprocal centimeters is just simply 1 over a centimeter in these cases, right? And so another, way that that's referred to is wave numbers. And so those then scale linearly with the energy, right? So if, something that's at 36,000 wave numbers is going to be higher in energy than something that's at 30,000 wave numbers. And, that's, and then if you're like, okay, right, if we subtract those two and we get 6,000, wave numbers in difference, that then scales, right, directly the same as energy does, right? Because you can just simply then calculate what that how how that value relates to joules, and so forth. So but not like directly, right? There's like all the stuff, right? But it's a good proxy, and so it's not like a true energy unit, but it's one that's commonly proxied in, especially because it's just simply 1 over whatever the wavelength is, so that way you can see how the scaling actually matches. Because when you're looking at something that's going from 350 nanometers to 400 nanometers, right, it looks really close, but in terms of the energy, right, that energy difference gap is actually a lot larger. And so, a lot of spectroscopists use that as a way, so that way you can, properly scale and look at, how spectra actually compare in those cases. So, so the only way that you really have to like approach this, right, is that, if you do this right here and you plug in, 36,000 wave numbers into HC, right, you'll get an energy, and then you can go back again and convert it out, right? So if you have, excuse me. So, right. So if you have this in, this value right here, as 36,000 wave numbers, that's going to be 1 over lambda. All you have to do is just simply, flip that over, right? So 1 over lambda, can be converted into lambda, right? And then you just simply have to go from there. So, if you have, 1 over 36,000 reciprocal centimeters, right, that ends up equaling, 2.78 times 10 to the negative 5th centimeters, right? That's the relationship there, right? So that wave number is equal to 2.7, a photon or whatever at 2.78 times 10 to the negative 5th, centimeters. And so then all you have to do is convert centimeters into nanometers. Excuse me. In these cases, right? So, what's the relationship? So we have, there's 1 times 10 to the 2 centimeters per meter. And then we have 1 times 10 to the 9th nanometers per meter, right? So if we want things to all cancel out, this has to get flipped. So now we just simply take 2.78 times 10 to the negative 5th centimeters is going to be multiplied by 1 over 1 times 10 to the 2. And then this is then going to be meters, centimeters, right? And then this right here gets multiplied by 1 times 10 to the 9th nanometers per meter, right? So centimeters cancel, meters cancel. You only end up with nanometers, so that comes out to being 2.78 times 10 to the negative 5th times 1 times 10 to the 9th divided by 1 times 10 to the 2, which comes out to 278 nanometers, right? Which is what I have in the answer key. So that's the relationship, right? So when you get into orgo and you start doing IR spectroscopy, right? IR spectra are reported in wave numbers, right, which is reciprocal centimeters. Right, and a lot of UV vis spectra by spectroscopists are typically also reported in wave numbers, because again, they scale directly with energy, right? It's not the same as with wavelength, where everything kind of starts to contract closer and closer, even though the energy differences are larger, as you go lower and lower in wavelength, right? The energy difference between something that's like 10 nanometers to 20 nanometers is much larger than the energy difference between something that's going from 500 nanometers to 510 nanometers, right? And that, because it's in nanometers, right, because it's in wavelength, that relationship doesn't really show as well as if you were to convert it into an energy unit, or in this case, right, like a proxy energy unit, where you just simply do 1 over the wavelength. Excuse me. All right, so C, 60 hertz to joules, right? So that equation is just simply going to be E is equal to h nu, right? So you just simply plug in Planck's constant, so 6.626 times 10 to the negative 34 joules seconds. You multiply that by the frequency that you have, right, by 60 hertz, and a hertz is a 1 over a second, right? So you just multiply those two and you get what the energy is in joules. Nanometers, right, you would use this equation right here. Megahertz to millimeters, right, that's just going back to this guy. Gigajoules to megahertz, right, you just simply rearrange this equation up here. And then 35 joules to centimeters, right, same thing right there, right? So you just simply, rearrange those. I'm not going to go into more detail on those specific parts.